Welcome back to our series where we are talking about portfolio optimization using Python. So last video, we walked through what is going to be happening behind the scenes when we're running our Monte Carlo simulation. And in essence, basically what we're going to be doing is we're going to be calculating random weights. So just a bunch of different times, we're going to randomly choose some weights. With those weights, we are then going to calculate the expected return, the expected volatility, and then the Sharpe ratio. With those different metrics, we're going to basically have a giant array of just different possible outcomes with random weights and stuff like that. And once we have that full array of simulations, what we're going to be doing is basically grabbing the maximum Sharpe ratio, so the risk adjusted return. And then additionally, we are going to be grabbing the minimum volatility. So we're going to basically grab two different, metrics. One is, hey, this is the portfolio with the lowest expected volatility. And then this is the portfolio with the highest Sharpe ratio. So with that being said, what we're going to do is we are going to start our little Monte Carlo simulation. And the first thing that we need to define is how many times we want to run this simulation. So define the number of times that we want to run the simulation. This is important because naturally the more number of simulations you want to run, the longer it's going to take. Now you want to make sure that you run it enough times to, get an ample number of simulations. It kind of depends on what you're trying to do. I've done anything from, 2,000 simulations up to 5,000. I mean, you could do many, many more. Ideally, the more times you run it, you should get more variety. And so naturally, you would expect kind of the better result, you would hope. So let's just say, 3,000 simulations. I'm just kind of picking a number, nothing super meaningful about that. And then what we're going to have to do is as we run through each simulation, we're going to have to store it in some type of array. And so what we're going to do is we're going to predefine some arrays, one for the weights, one for the returns, one for the volatility, and one for the Sharpe ratios. And they're basically just going to be NumPy arrays that are filled with a bunch of zeros. And as we run through the simulations, we're just going to fill in that array. So the first one is prep the weight array of NumPy zeros. So we'll call this one all weights. This will equal NumPy. We're going to do zeros. I don't know why I have two brackets. I don't really need two brackets. We're going to, I'll put on two just to be safe. Number of portfolios or number of portfolios. And then for our second one, it's going to be the number of symbols. I think it does actually take a tuple. So this is, we're going to have, X amount of portfolios times the number of symbols. If you go all the way up here, I think we have the number of portfolios somewhere up here. I'll have to double check. All right, no, number of portfolios is, I don't know why I'm doing this. Basically this one. So actually I will copy this and make that instead of simulations, I will say number of portfolios to be a little more consistent. And then we're going to do the same for the returns. So prep the returns array of NumPy zeros. Hopefully you kind of see what's going on here. This isn't anything I would say is super complicated. It's just a lot of prep work, a lot of prep work, just because we need places to store the values as we're running through these simulations. So this is just really just prepping some blank arrays. As you're running through it, you're going to just fill in each row and go on and on and on. So I'm hoping this isn't anything too crazy. Okay, NumPy zeros. So we're going to do one obviously for the volatility one as well. This one's going to be basically the same thing. Basically, these ones are going to be the same exact thing. So you could probably just do this with a one-liner as well, but just for a little bit of clarity and making sure that everyone understands what we're doing here. I'm really just creating some empty arrays. That's all I'm doing. And so this is going to be the same exact thing. Okay, so now comes the fun part. So now we're going to quote unquote start the simulation. And so what we're going to do is we're going to say for, we'll just call it index or whatever. We'll call it ind for short, in range. And then we're going to do number of portfolios. So you can see here, obviously, we're going to say, hey, do this, whatever we're about to do 3,000 times. And then basically what we're doing is we're literally just doing what we did up here. That's all we're doing. It's nothing, I would say, different in the sense of we're just doing it more times. So same logic holds. First, let's calculate the work, calculate the weights, and then we're going to say weights equals numpy array, and then we're going to do numpy random dot random, and then we only need the number of weights that matches the number of symbols. So this is a very important part. I think this is probably, without this line right here, it wouldn't work, right? So we're just randomly generating numbers on each iteration. I have no idea what they're gonna be. That's the point, is you just randomly keep doing it. Ideally, what's going to happen is as you get more and more samples, you should find kind of what tends towards the average, but more importantly, you should find what the max Sharpe ratio is and what the minimum volatility is. So basically, you're doing so many simulations that ideally you would identify what the optimal portfolio is. That's at least the general idea. Now, just like the previous video, we have to have this constraint, which is, you can't have more than 100% of your portfolio allocated. So this is making sure that it's going to be 100% allocated and it's not going to be higher than 100%, because otherwise it's kind of pointless, right? So then add the weights to the quote unquote weights array. So nothing too complicated here. We're going to say all weights. We're going to do our square brackets. We'll do the index, and then we're going to say, hey, do all the columns. So we're just basically adding that row into it. And then we're basically doing the same exact thing with the return and the volatility. So calculate the returns. And so here, or the I'll call it the expected log returns. We will say return array, more array stuff, right? It's kind of funny. I was doing some Panda stuff yesterday, and I don't know what it is. I just can never remember the syntax for pandas if my life depended on it. It's just one of those things where it's like there's so many different ways to do the same thing. I don't know why. I can never remember doing like basic things, like literally just selecting rows. I had to look it up again. I was like, why do I have to keep looking up? So here we're doing what we did before. We're going to calculate the log returns. A lot of people ask why log. Logs are better for time series. So that's the important part. And then we're going to say, okay, here's the return for each item times that particular item by its weight of the portfolio. So for example, if 20% of my portfolio is Microsoft, then I want to take the idea of taking the total return and saying, hey, well, what portion of that actually is contributing to the portfolio? And then additionally, that 252, we annualize it. So we're annualizing our returns. A lot of times in finance, you want it on an annualized basis. So that's basically what we're doing here. All right. And calculate the volatility. Yes, and then add them to the the array. Okay, so this one is a little bit more complicated. I would say in terms of just math behind it. I mean, when you look at it, it's nothing too crazy, but I think writing it can intimidate a few people. So again, we're going to take the square root, dot product. We're going to do weights. We're going to transpose those weights. We're going to do another dot product. So we're going to times transpose weights by the dot product of the log return. We're going to take the covariance of it times, again, 252. And then we're going to times that by the weights. again, people kind of ask, like, this seems like, what is going on here? Why are we doing all this? Logic is still the same. Remember, we want each piece of our portfolio to contribute to the total portfolio evenly, or at least based on how much they actually represent of the portfolio. So this should make sense in the sense of, hey, this is how much volatility that particular instrument is contributing to the overall portfolio. That's how I look at it. So you're just saying add up all the different contributions. And then we have to kind of capture this idea, which is you can have assets that are correlated with each other. And so this is capturing that. So this is saying, hey, this is another piece of that volatility where we're not just looking at them individually. We're saying, hey, how are these instruments correlated with each other? Because that is also considered some form of volatility. So we're going to put those together. And once we do that, that's basically what we're going to get out of it. So that's going to add our volatility. Finally, we can calculate the Sharpe ratio. And then what we're going to do here is we're going to do the Sharpe array. We'll do the current index that we are on, and then it's going to be the return array index, and then volatility array, and then that index as well. We'll say points, I don't know, just 0.1, I guess, to make things easy. We'll just do something like that. And then we'll add them all together. So we'll combine them. All together. And so we're going to say simulations underscore data equals a master array that contains our return array. It's going to contain our volatility array. It's going to contain our Sharpe array. And then it's going to also contain all of our weights. So this is kind of our master data set. And then we'll create a data frame from the master array. So nothing, again, hopefully too complicated at this point. We're just going to create another data frame. We're going to use pandas. We'll use pandas.data frame. And then from here, I'm going to pass through my simulations data. Important thing is we do need to transpose our data frame just to get it all set up the way we need it. Because when we put it in there, it's not going to look right. So when we transpose it, that's fine. And then add the column names. And I think for the most part, yeah. Okay, so some of this it's just more typing than anything. So I'm not going to spend too much time on it. I will show you what one important thing is. I want to make sure that we have this. So this is just simply taking our data frame. We're going to call it columns property, and we're going to set that equal to a list of the new column names. That's all that's doing. So this is just simply giving our data frame some column names. Then from here, when we're adding the data into our data frame, we want to make sure that everything has the right data type. So unfortunately, what happens is like the strings that should actually be floats, they're not floats. So this, what I do is I take our data frame and then we use the infer objects method. And this is kind of just a little quick way to infer the data types. And we reassign it to this new one. So this is just simply making sure that if we have a string and it's supposed to be a float, that it's a float. And then from here, I'm literally just printing it out again. So again, nothing hopefully too complicated here. I think if we've watched the other videos, that should make a little sense. I do have to run everything again. So I'm going to run this. And FYI, 3.9, Python 3.9, I installed it yesterday. So you might want to take a look yourself. It's kind of interesting. They've added in a few different things here and there. So, give yourself a chance if you haven't already. Maybe install it. All right, so let's run this. Now, again, keep in mind, we're doing a bunch of simulations. So has attribute name? What do you mean? Oh, let's take a look. Simulations, DF, modules, pandas has no attribute names. What does that mean? What is that supposed to mean? Let's run it again. Okay. Let's do this. Let's put the simulations df equal to simulations transpose. Let's try that maybe. I'm hoping. Let me see something. Pandas is PD. Okay. That seemed to work no problem. So I don't know why this is all of a sudden not working. It should work. Let me make sure I'm spelling everything correctly. Seems to work fine with me. Okay, pandas has no attribute data frame. Oh, data fame. Oh, I'm sorry. God, why did that take so long to find? That should have been obvious. Sorry about that. Okay, so we have our simulation results. So it looks like everything came out the way we wanted it to. You can see, obviously, we have variation in our results, which is expected, right? We're randomly grabbing some weights. So naturally, what we're saying is, well, what if I tweak this one a little bit or I tweak that one a little bit? How does my return change? How does my volatility change? The idea here is if you tweak it enough times, you should be able to find what the optimal value is. So let me see what, yeah, I think we could maybe do the next one. Let me check really quickly. I don't want to portfolio. Let me check this. Yeah, okay, we'll do that. So we'll calculate, we'll just grab two important ratios. So one is the max Sharpe ratio. So grab the max Sharpe ratio. This is obviously the portfolio where the weights gave us the best Sharpe ratio. So the highest Sharpe ratio. So if our goal was to create a portfolio that had the highest Sharpe ratio, then what we're saying is we would want to use these particular weights. So I'm going to take our simulations df. I'm going to find the location where the Sharpe ratio column, so the Sharpe ratio column is the max. So the max. So I'm finding the row inside my data frame where the Sharpe ratio column is the max. That's all this line is doing. We're going to also return the minimum volatility. So let's say for a second, I want the portfolio with the least amount of volatility. I'm also going to find that as well. As you guessed, it's going to look very similar to this. All we're doing is we're now saying, hey, instead of looking at the Sharpe ratio column, why don't you look at the volatility column? And then instead of finding the max volatility, because we sure as heck don't want that, we want the minimum volatility. And then from here, I'm just going to print it out. So this is just doing a little bit of cleaning up, nothing fancy. What does that look like? Did I misspell it? I did misspell it. I always misspell it. Okay, so let's take a look. The portfolio with the highest Sharpe ratio has these combination of weights. Let's take a look and see kind of how this is distributed, because remember, we have Apple, Microsoft, Square, and Amazon. So basically, if I'm looking at this, what it's telling me is have a substantial amount in Apple, have very, very, very little, almost nothing in Microsoft, have a tiny bit in Square, and have a big chunk in Amazon. And then if I'd followed that rule, this is what my Sharpe ratio would be, this is what my returns would be, and this is what my volatility would be. So that's basically that. Let's imagine for a second that I want the lowest volatility. So I want very, very little volatility. So if I follow these weights, this is how I need to distribute it if I want lower volatility. You notice how it kind of flip-flopped a little bit. So now all of a sudden we are still keeping, relative decent size of Apple. Microsoft jumped up. Square jumped up a lot too. But then Amazon went down pretty dramatically. So that could be an indication. Maybe Amazon, it might give you very good risk-adjusted returns, but it does increase your volatility. It might just be more volatile potentially. Who knows, right? And then again, we can see our returns as well. And with that, I will cut off the video here. So if you have any questions about running through the Monte Carlo simulation or how to interpret the output from that simulation, feel free to put that down in the comments below. Otherwise, in our next video, we're going to do some plotting, and then we're going to also do a more quote-unquote efficient simulation where we can find the optimal values that we need. Now, with that one, it's a little bit longer just because we have to define some functions and all that kind of stuff. So I would say we probably have like maybe 2 videos left, and then we should be good with this series. So again, if you are new to the channel, feel free to subscribe. And then if you are a current subscriber to the channel, feel free to like the video if you found this was helpful. If you have other suggestions for different topics, feel free to put that down in the comments below. And if you have anyone who you think might benefit from watching this video, feel free to share it as well. Again, our goal is to get to 20,000 subscribers. I never thought I would be saying that. Whoever thought 15,000 people would want to watch my videos? I sure as heck didn't, but hey, it happens. So thank you again for watching, everybody. We will see you in the next video.